The nephron. So I gave you an overview of the anatomical structures, and we went specifically over the functional unit, which we call the nephron. And looking at the nephron, we're going to focus specifically on our vessels, and let me pull up a slide that will help kind of sum that up for us. I'll be specifically looking at this was our simplified nephron that you were able to see. And we want to focus specifically on the nephron. Here you can see the renal corpuscle, which is going to have our glomerular or Bowman's capsule. And this is going to be the beginning of filtration, where we're going to have fluid moving from the capillaries, and the capillaries supplied by the afferent arteriole to the glomerular capillaries back to the efferent arteriole. We get filtration that takes place that's going to push fluid out using those pressures that we discussed on Tuesday, namely our glomerular blood hydrostatic pressure minus our capsular hydrostatic pressure minus the blood colloid osmotic pressure. That gives us a net pressure of 10 millimeters of mercury that pushes fluid out. So this is going to be our preliminary urine. This is our filtrate that comes out. And remember from the structure of with the structure of the glomerular capillary, specifically the visceral layer of the visceral layer of the glomerular capsule, you saw the presence of our podocytes. And these were structures that have these pedicels that reach out and they create these filtration slits. And these filtration slits only allow small molecules out. And so those small molecules that you're going to be able to see are going to be our ions, you'll see water, sugar, but any of the bigger stuff, their cells, our bigger proteins, are going to remain within the circulatory system. Okay? So anything that doesn't get filtered out in the glomerular capillaries makes their way back into the efferent arteriole, which is going to circulate back out and wrap around, excuse me, it's going to wrap around the rest of our tubule, which will start the process of reabsorption. So whatever stuff we've pushed out, remember, we've pushed out a lot of water, we pushed out a lot of glucose, we pushed out a lot of ions. We want to be able to pull that stuff out. Because if you end up peeing this out, we're going to end up losing about 150 liters per day. And that's not what we want. We want to be able to reabsorb the stuff that's absolutely necessary. And how much we reabsorb is going to be dependent on certain things. We're going to be looking at whether the sympathetic nervous system is fired up. We're going to be looking at blood volume. And that's stuff we're going to be examining today. Reabsorption as it takes place down the renal tubule. And the areas that we need to look at for the renal tubule, we'll be specifically looking at the proximal convoluted tubule. We'll look at the loop of Henle, the distal convoluted tubule, and then the collecting duct. And we'll be able to look at reabsorption as it takes place. Because as you can expect, it differs from section to section. Not only are we looking at things that are close to the glomerulus, you're going to see the convoluted tubule, you'll see the distal convoluted tubule. You saw also on Tuesday that the distal convoluted tubule comes back and provides feedback to the glomerulus by virtue of the macula densa. The macula densa has chemoreceptors that detects the content of the filtrate by the time it makes its way over to the distal convoluted tubule. Then it can provide some feedback saying, well, it doesn't look like you have enough fluid coming out, so let's do some readjustments here so that by the time that fluid makes its way back, it's going to correct itself. That's all part of the renal autoregulation that we learned about on Tuesday. And then as we go through, so what you can be expecting is reabsorption taking place throughout the entire, we're going to be absorbing a lot of water, reabsorbing a lot of glucose, reabsorbing a lot of the ions, namely our sodium, our chloride, a bunch of stuff that we'll talk about as we make our way down, so that by the time we make it to the end of the collecting duct, down to the papillary duct where the renal pelvis is. Remember, our renal pelvis is where the renal artery came in, the renal vein came in, as well as that concentrated urine. Doctors typically call this the sort of bladder of the kidney. This is where you get the most concentrated urine that comes out that's going to get excreted out or urinated out. So looking at that 150 to 180 liters that gets filtered out, you'll be able to see how we reabsorb all the way through to produce that concentrated urine that you produce on a regular basis. So that should provide a good overview of what we talked about on Tuesday. What we're going to do is going to continue on. We've already talked about filtration. Let's take a look at what happens with reabsorption all the way through. The last thing I didn't quite mention is secretion. So not only are we going to be reabsorbing, but anything that's also present in the blood that wasn't reabsorbed, that wasn't filtered out, may get secreted out at different areas of the tubule itself. So this is the formation, this is the presence of what's called secretion. So in effect, looking at how to sum up urine, as I mentioned on Tuesday, what's actually urinated is what's filtered minus what's reabsorbed in the tubule, reabsorbed, minus that of what is secreted back into the tubule. And that's going to give us a concentrated urine, or maybe even a dilute urine. That really inherently depends on how much blood volume, how much water you've had to drink. Okay, as you know, this is probably fairly obvious to you. If you drink a bunch of water, you may notice you probably have dilute urine. If you haven't had any water, let's say you wake up in the morning, you're fairly dehydrated, and you urinate, you may notice that it's probably dark in color, probably has a very strong odor to it. So you can see the different composition in your urine, and all that depends on, number one, your salt content, but number two, mainly the amount of water that you've had to drink. All right, so with that, we're going to move past our GFR regulation, our glomerular filtration rate, and we last talked about kidney disease. Now we're going to focus back on tubular reabsorption. Okay? So as I mentioned on Tuesday, filtration takes place in the glomerular capillaries. But not all is filtered out. That doesn't mean that all the plasma and all the water and all the ions gets filtered out. You get a good chunk of it that gets sent out, but you're going to now have this thicker blood that makes its way through. Okay? So it's this duty right here. This is the stuff that's going to return back into the renal vein down the line. And so when we go for the peritubular capillaries, we're going to want to reabsorb all that fluid back from our preliminary urine or filtrate and so forth. So we'll talk about this point here. So now that gives you an idea of what's present. You know that we've got red blood cells, we've got large proteins, we've got smaller proteins, we've got hormones, stuff that's present in our efferent arteriole. Now that you know the compositions in our filtrate versus our what's present in our efferent arteriole, let's take a look at, once again, our arrangement. You have our proximal convoluted tubule, again, proximal because it's closest to the glomerulus, loop of Henle, which dips out into the medulla, which is more the core of the kidney. We're going to loop right back up. Here we have the descending limb, and then we have the loop, and then we have the ascending limb. As you can expect, we're going to see different characteristics to the structures of these different loops that will lend itself to the different absorption that takes place down in the descending arm versus the ascending arm. We'll curve right back up into the distal convoluted tubule, then back down the collecting duct. Okay. Now that talks about the movement of the filtrate to urine, but we also have to talk about the capillaries. And the capillaries that are present. Here we have our efferent arteriole, and then we're going to wrap around this whole thing. Actually, technically, let me redraw that. And notice I am kind of drawing a little bit backwards in that area. You're going to see the peritubular capillaries. So we go from the efferent arteriole back to peritubular capillaries, where we come in and allow the collection. So you literally have these capillaries that wrap around that assist, well, not necessarily assist, but they are the end point for reabsorption. We're reabsorbing stuff from the filtrate back into the capillaries. And I did draw it a little bit backwards over here. I did go from the proximal convoluted tubule back to the ascending limb, back down this way, back to the descending limb. and back up and around. And you'll see that as I drew the filtrate moving down this way of the loop, you see that blood will flow the other way. And I'll have a term for that that'll explain that later. Now, the difference between the paratubular capillaries and the vasa recta is just really by the nomenclature. Paratubular capillaries represents the capillaries surrounding the entire nephron, namely the PCT and the, I'll call them the PCT and the DCT. The vasa recta is the capillaries surrounding the loop of Henle. Again, just a naming convention. There's a little bit of an anatomical difference, but that's really a moot point. Now, tubular reabsorption. How much do we reabsorb? About 99% of what was present in the glomerular filtrate is going to be reabsorbed. So as I mentioned, about 150 to 180 liters per day. And we're going to reabsorb 99% of that, which is going to bring us to about 1 to 1.5 liters per day in urine. So we're going to have to reabsorb a lot. And what are we reabsorbing? Again, things that were filtered out in the glomerulus. Glucose made its way through, electrolytes, vitamins, water, amino acids, and any other small proteins that made its way out of the glomerulus need to get filtered back into the capillaries. And where does most of the reabsorption take place? Right in the proximal convoluted tubule. It should make sense because this is really the first output. From the glomerular filtrate, we're going to go through the proximal convoluted tubule. How much of it's going to get absorbed by the end of the proximal convoluted tubule? About 65% of it. So almost 2/3 of the stuff. And what stuff am I talking about? Mostly water. Along with these other essentials that I mentioned on the prior slide. Sodium, chloride. We're going to have bicarbonate, glucose, amino acids, and those vitamins are going to get reabsorbed. So about 2/3 of that will be reabsorbed. Notice that on the slide to the right, and this you can reference because I really particularly like this image because it helps you point out different areas. Again, here's our glomerulus. Here you can see the PCT. Here's our DCT. Here is our loop. And then our collecting duct. And this slide talks about things that are going to be reabsorbed in blue and our secretion that's going to take place in green. So this is a really good summary. And at the very end of this section, I also do have another good summary in the form of a table that pinpoints where reabsorption takes place and where secretion takes place. So like I said, 2/3 of the stuff that I mentioned here get reabsorbed in the proximal convoluted tubule. But there is a little bit of secretion that takes place as well. Hydrogen ions, you'll see ammonium, stuff that we get rid of, and then also some drugs here. And I don't really point out any drugs that are reabsorbed here because I know there's, some drugs that are secreted at this point. But any things that we do need to get rid of, some are eliminated at this point. The other portions I'll talk about when we get to the loop of Henle. You'll see the key difference, and again, I'll talk about this later. The descending, you'll see the reabsorption. Water. And that's the only thing that's reabsorbed in the descending limb. In the ascending limb, the only thing we're reabsorbing, salts. Sodium, potassium, and chloride. So that's going to be the main difference. But the big chunk of where we reabsorb is in the proximal convoluted tubule. The next thing to look at is when we make our way into the DCT. Again, a quick gist of reabsorption. Salts are reabsorbed, sodium, chloride, and calcium in the DCT. And then in the collecting duct, more salts. We're reabsorbing salts and we're reabsorbing water. So that's really the big chunk of it. So if you're looking at where we're reabsorbing most of the stuff that we were able to absorb through digestion, really in the PCT. And then everywhere else, we're fine-tuning and adjusting. And so, again, depending on water levels, depending on electrolyte levels, you're going to see that hormones are going to come into play that will alter the composition of the urine through reabsorption, especially towards the latter end, the DCT and the collecting duct. So let's take a look on the next slide over, looking at water reabsorption via the osmotic gradient. And the key thing about this slide, if I could summarize this in a couple words, is that whenever you have salt move out, let's say salt being reabsorbed, water typically follows with it as well. So let me show you a diagram, or at least let's start to draw out a diagram that we've always seen. And I always reference this YouTube because it's very physiologically relevant. And as I mentioned earlier, we have our solutes in our solution, and on the other side we've got less solutes. Let me just draw 3 on this one, and I'll draw, I guess it really doesn't matter, let me draw like 6 or 7 of them on the left side. So on our left, we're going to have a hyperosmotic, and on the left, hypoosmotic in relation to one another. So the direction of osmosis, well, you guys answer that. Which direction would you see water moving? Would you see it moving to the left or moving to the right?
To the left.
To the left, right?
Yes.
Why is it moving to the left? Mainly because it's trying to, again, equalize the concentration on both sides. Here you see a lot more solutes on this side. Over here, you see less solutes. So in order to balance out, osmosis wants to move over to the left. Okay, I'm not going to go into hydrostatic pressure because that's not really the focus, even though that does apply. So if I were to, now looking back at the semi-permeable membrane, every time I've talked about the semi-permeable membrane, I've always said that the solutes don't move. But what if I could get those solutes to move? What if I could transport some of these solutes to the other side? And let's just say, due to osmosis, we see the water levels move, we see the water levels rise up to that point, and the water levels, we'll bring the water levels back, no, don't get rid of that. We'll bring the water levels back over here. So now the concentrations are balanced out. We've definitely got more water over here. This whole thing is in now net osmotic balance. We have equal amounts of water moving to the left due to osmotic pressure. We have equal amounts of water molecules moving to the right due to hydrostatic pressure. Now, as I mentioned, this semi-permeable membrane, if I could move solutes over, and I can move them over, if I can move that solute over from the left over to the right, which direction would water move?
To the right.
It'd move over to the right. So anytime I'm going to start pushing those solutes over, now water wants to move back this way. And that's exactly what you're going to be able to see through reabsorption. The general principle, especially in the proximal convoluted tubule, you're going to see coupling of the movement of salts. Anytime you move salt across, water is going to want to move as well. Okay, so that's coupled movement. And that's exactly what we're talking about with this slide, is water reabsorption due to the osmotic gradient. Whenever we move salts or any of the ions across, that's going to allow this, it's going to increase the osmotic gradient as we've been able to do on this image to the top. This whole movement of water is passive. I'm not using ATP to move water across. The osmotic gradient is just increasing the tendency for water to move over from the left to the right as we move solutes over. And now, water will move through osmosis and it'll diffuse across that semi-permeable membrane, but what's going to enhance the movement of water? How do I get water to move faster through? Again, from our tissue lecture, way back when, if you can recall, I mentioned aquaporins. Aquaporins were water channels. So the presence of aquaporins helps water move faster. Okay? So with that, all I would need to do to get water to move across is to build out some aquaporins. So you're going to be able to see a hormone that's going to come in and activate these aquaporins. It's going to create aquaporins that will increase these channels to shuttle water across. Because it's exactly what we want to do for reabsorption. We want to be able to reabsorb water fairly quickly. We don't want it to just diffuse across and trickle through. We want to move it. Okay? And where is that going to take place? Namely in the proximal convoluted tubule as well as the loop of Henle. All areas that we'll talk about in just a bit. So in this image to the right, here you can see the movement of salts, our sodium and our chloride, and then you're going to see water following as a whole. So that is what's taking place. And so reabsorption, when we talk about the reabsorption of all the stuff that we've just talked about, when we look at sodium chloride, bicarbonate, glucose, amino acids, and vitamins, we're going to have to be able to move these solutes through both active and passive means. Again, active. What did active movement require? Active transport required one specific molecule that I quizzed you guys on. What was that?
ATP.
ATP. We have to use ATP to shuttle it across against its concentration gradient. In passive transport basically is just moving down its concentration gradient from a high to a low concentration. So with this, you're going to have to be able to take a look, we're going to be able to look at the different transporters that we have to move these ions across. So again, in the proximal convoluted tubule, move these ions across and water will follow. So ion transport is what we'll talk about the next couple slides over. Water will just follow along down its osmotic gradient. Again, moving salts over, moving ions over will cause water to move along as well. All right. So which things are we going to be looking at? Again, sodium, chloride, we'll be looking at calcium. To a certain degree, we'll look at hydrogen ions. This is going to be more related to acid-base balance. This is our bicarbonate. That you should be familiar with by now. Phosphate is going to come in also, and I will point that out, although I won't really require you to remember phosphate. You'll also see sulfate come in as well, and ammonium. All right, so let's take a look at how this takes place. So from many slides from this point on, you're going to start seeing these types of images. And to quickly orient you what you're looking at, you're looking here at the lumen of the tubule. You're going to be able to see the epithelial cells, our tubule cells. Here you'll see the interstitial fluid, which I'll name IF. And that interstitial fluid, all this will consist of the extracellular fluid. And here in the peritubular capillary, obviously this is our capillary. So the direction of reabsorption is always going to move from left to right in these cases. We're trying to reabsorb fluid as well as all the stuff that we've mentioned, all of our salts, sodium, chloride, everything else is going to move from left over to right and reabsorbed into the capillary. So there's only two ways to be able to get stuff across. Either you get it in between the cells, which we call paracellular reabsorption, or we get it through the cell, which we call transcellular reabsorption. The mechanism behind paracellular reabsorption is basically in between. And here you have our tubule cells, which are connected together by tight junctions. It does allow things like sodium to move across. It holds fairly tightly, but sodium can leak across. And typically in this case, we're going to move from a high concentration over down to a low concentration. There's no transporters, there's no leaky channels or anything like that's present at that tight junction. It literally will just flow right in between the cells and leak right through. So this typically is, or in all cases, going to be utilizing passive transport. Again, this is all taking place in the proximal convoluted tubule, but specifically within the first half of the PCT. So we'll be looking specifically at the movement of ions. Now, stuff that moves across the cell is transcellular reabsorption. And the way we'd have to get sodium across the cell is to shuttle it across. So where we would see the level of sodium, and again, remember where we had in our generic cell, when we talked in cellular physiology, where was most of our sodium? Think of the generic cell. Where was most of our sodium? Was it on the outside of the cell or the inside of the cell?
Outside.
Outside of the cell, right? So in order to get that sodium out into the outside, we had to utilize a pump. And what pump did we use?
Sodium pump. Sodium
I
pump.
heard potassium, I heard sodium. Sodium-potassium pump, right? So we had to use ATP to pump sodium against its gradient from a low concentration over to a high concentration. As we move from a high concentration, now we can shuttle that sodium, which is now high in the interstitial fluid, out into the capillary. So as I start shuttling things across, now sodium, which is high in the lumen, can now just diffuse across. So this is going to be a form of passive. We're going to be able to see that sodium can now diffuse across down its gradient from high to low, and then from low to high. So all this employs both passive and active means to get things across. And again, all this slide talks about is just sodium. But the key thing with sodium is that whenever we move sodium, there's going to be a bunch of symporters and antiporters. These are typically called cotransporters. Cotransporters means if I'm allowing sodium in, well, in the case of a symporter, if I'm going to allow sodium in, I'm also going to allow something in as well. It takes two to basically move through from the extracellular fluid, in this case the lumen, out into the cell. An antiporter means sodium in and something else moving out. So these are the different gates that we're going to have to get things across. And again, all this taking place in the proximal convoluted tubule. The symporter in this case would require movement of sodium at the same time the movement of glucose. So this is our way of getting sodium in and glucose in. And glucose will then move down its concentration gradient across this transporter, and it'll go from the glucose will go from inside the cell into the interstitial fluid into the capillary. Again, we'll see our sodium-potassium pump where we got sodium into the cell. Now we got to pump sodium back out into a high concentration back into the capillary. So this is an example of two things moving together, sodium and glucose. The antiporter you're going to be able to see on the next slide over. And in this case, let me just quickly describe what's happening. Sodium going in, hydrogen going out. And that should make sense, because think about what we're doing. Again, reabsorption moving over to the right. We want to reabsorb, we want to conserve sodium, but we want to get rid of excess hydrogen ions. So this is a form of secretion. We're dumping stuff into the lumen. But we're not just dumping hydrogen ions. Hydrogen ions don't just sit around in the blood. Right? They don't just sit there freely float across, and we're not just having it diffuse across into the lumen. How do we carry hydrogen ions in the blood? There was a buffering capacity that I remember. There was a particular ion that I talked about that buffered hydrogen ions. Bicarbonate ions. Okay? So bicarb is present in the blood, and it picks up hydrogen ions, and it carries it. And in that process of carrying it, you're going to see how we eliminate specifically in the proximal convoluted tubule. So I know this looks a little scary. It's because it is. And we'll see it over on the right. And I want to go specifically into this particular antiporter. Now, I won't test you guys on the extreme mechanism of how this takes place, but at least you can still gather some principles from here. And what I'm first going to start off with is, again, the antiporter. Here I'm going to have sodium going into the cell, and that's what I'm first going to start off with. And I'm going to end with hydrogen ions leaving. So the general principle here of what we want to do is we're going to be able to see hydrogen ions that are carried in the blood. And this is where we have bicarbonate. Bicarbonate, we need to replenish and get bicarbonate back into the blood. CO2 is something that's typically generated. If we have a bunch of hydrogen ions being produced, we know we're typically undergoing glycolysis, and we're probably going through a lot of glycolysis, and that's pushing a lot of lactic acid into the blood. That acid gets buffered by bicarbonate, and as a byproduct, we have a lot of CO2. And that CO2 gets diffused into the tubule cell. Not only is it coming from the peritubular capillary, it's also coming from the interstitial fluid. The third place where it's being produced, we've got a lot of the cell producing a lot of CO2. Why is that? You guys already pointed out that the sodium-potassium pump is churning out, is using ATP to fuel active transport. So if this cell has to continually generate ATP in order to transport sodium across, it's undergoing cellular respiration. And in the process of undergoing cellular respiration, we're producing a lot of CO2. So we've got CO2 coming from all over the place. And with CO2, once you get CO2 and you get water together, water that's already present in the cell, those two come together. So CO2 and water form carbonic acid. And carbonic acid dissociates into hydrogen ions and bicarbonate. So what's happening is that CO2 and H2O bind together. They form this weak acid called carbonic acid, and carbonic acid will split. And that split, where bicarb now diffuses down its concentration gradient back into the capillary. So that should make sense. If I've got a lot of CO2 in the blood, I've got a lot of hydrogen ions, what better way to pump bicarb back into the capillaries? Now what happens with that excess hydrogen ion that we split from that carbonic acid? That hydrogen ion then gets pumped out through the antiporter and gets secreted back into the tubule. So that should satisfy what we've just talked about. That's sodium reabsorption, which we saw, and hydrogen ion secretion. But that hydrogen ion isn't done yet. What we can do with that hydrogen ion is it also gets buffered. It gets buffered, and one thing I neglected to mention here, that what catalyzes the reaction of CO2 to H2O, CO2 and H2O into carbonic acid, carbonic anhydrase. That shouldn't be new to you guys, that you've seen several times now. Now, there's also carbonic anhydrase that's present on the outside of the tubule cell. And when that hydrogen ion comes in, any of the bicarbonate that was not filtered out, that made its way through, going back to an earlier slide, I don't know how far back I have to go, any of the bicarbonate that was not filtered out still makes its way through. Okay? I'm sorry, no, sorry. Any of all the bicarbonate that actually did get filtered out, let me reverse that. Any of the bicarbonate that does also get filtered out that's present in the lumen also gets buffered by bicarbonate. But that bicarbonate then forms carbonic acid. That splits off. You get now water and that CO2. That CO2 comes in and fuels this whole system again. So this is our way of, once again, driving more bicarbonate back into the blood. So in these slides, this really points out the apical side. This is what's happening on the apical side. This is what's happening on the basilar side. And this is what's happening in the cell. Karina, you had a question?
So how did you get the CO3 from, okay, so the
Which one?
hydrogen, no, on the bottom one.
Yeah.
That one, yeah, that one.
This CO2 right here?
The top one.
The
H2, oh, the bicarb, yeah.
Where did that come from? That's what's already present in the lumen.
Oh, okay.
Yeah, so you have bicarbonate that's already present there. All we've talked about is the movement of sodium and the secretion of hydrogen ions. Going back to this earlier slide, let me go back to what's already present in the filtrate. Bicarb is right there. Okay. Did that answer your question?
Yeah.
So this process helps conserve that bicarbonate. Any of that bicarbonate that we would have lost in the filtrate also gets reabsorbed and pumped back into the capillary. It just has to go through and get transformed a couple times back into CO2 and water, and then back out through carbonic anhydrase. So in essence, carbonic anhydrase facilitates the reabsorption of bicarbonate across. Yes? Carbonic anhydrase facilitates the movement or the transport of bicarbonate from the lumen into the cell, back into the capillary. So when you look at these particular slides, what will help you look at this is start off with the main idea. Well, really not the main idea, but just look at the caption. HCO3 reabsorption. locate where that bicarbonate is and follow the path. CO2 gets back into the cell. This is the intracellular mechanism where carbonic anhydrase converts it back into carbonic acid, splits it off into hydrogen ion, which flows right back out. Bicarbonate gets pushed back in and reabsorbed back into the capillary. I know it looks a little scary, but again, start off with what you're looking at. And here, the same process. Start with your sodium, end it with hydrogen ions. And once you kind of follow it once, twice, 3 times, 4 times, however number of times you get it, you'll see it. But the main idea, again, is to just look at how we shuttle things across the apical side. And as a change of pace, look at the apical side. What do you guys notice about the apical side? Is it straight? No. It's got villi on it. And the microvilli that are present on the apical side, just like that quiz question I asked you guys, increases the, well, did I ask that quiz question? Yeah. I think it was about the small intestine. Yeah, there you go. So, well, in essence, remember you had the plicae circularis. Here you have then on top of that you have the villi, and on the villi you have the microvilli. The microvilli basically increase surface area, and that allows for increased surface area for absorption. Same principles once again. All right. So that, again, just a quick recap. Symporter and antiporter, things that get sodium. As we get sodium into the cell, into the peritubular capillary, we're going to move things through as well. So the last thing we're going to see is passive transport. And the main idea behind passive transport is looking at electrochemical gradients. This whole time, every time we're pushing sodium across. When we push sodium across, sodium has a positive charge. So if I'm pushing a positive charge into the cell and then pushing it out of the cell, I'm going to have other things follow as well. And what things am I going to be talking about? Chloride. Anytime I have a positive ion move along, you're going to have a chloride follow along with it. And sodium, NaCl, both combined together, table salt, right? This is our way of conserving salts. So the second most abundant ion would be chloride, the first being sodium. So the main idea here is utilizing an electrochemical gradient that allows the movement of other ions as well. So I don't go into the mechanisms behind this. I've talked about sodium. There's different mechanisms for each of these: potassium, calcium, magnesium, urea. I'm not going to get into those. But the general principle, sodium moves across, chloride will follow as well, and it'll move in between through the paracellular route or the transcellular route. Again, reabsorption that takes place down the line. So what's taking place in the first half? Movement of salt, movement of sodium. What's taking place in the last half are the other ions. So not only are we moving the ions, but we're also establishing an osmotic gradient. Again, general principle, move a bunch of salts, move a bunch of ions, we're going to get water that moves across as well. The one thing I won't get into too much detail here is urea. Urea kind of comes in as well. Urea, again, is a byproduct of the breakdown of amino acids. Again, not to go too much into detail again, but the structure of an amino acid has a carbon here, and this carbon is attached to a carboxylic group, and a functional group attached. And here the deamination involves the breaking apart of this particular bond, which releases NH2. And NH2 is our amine group, and then mix that with a hydrogen ion, and that creates NH3+. NH3+. And that is ammonia. And ammonia then gets broken down into ammonium, and then ammonium through this process creates urea. So urea is a particularly small molecule that's all involved in this. Basically what it's doing is it's trying to maintain this osmotic gradient. So I won't go into too much detail about it, but if you see reabsorption and you see secretion later on, it's a concept, if you ever want to get into more detail about it, it's called urea recycling. It's a way of being able to push water along and kind of hurry it up along. Okay. So the concept here, looking at all of this right here, as again, a recap of what we're talking about. Here you can see a recap breaking all of this down. I won't go into too much detail again because this is basically a reiteration of everything we talked about. But the movement of sodium also allows the movement of other ions and other molecules. We use our sodium-potassium pump to pump things across. We get potassium that comes in as well through that sodium-potassium pump, but can also leave as well. And gets either pumped back in and then pumped right back out through leaky channels. There's a coupling that takes place between these two. So both salts, both sodium, calcium, glucose, amino acids, anytime we move ions, we move water as well. So it's safe to say that that osmosis is coupled with active and passive transport of all of these molecules. Key word that I want to illustrate here is coupled. Kind of married together through that general principle. Other things that you'll see that's also taking place in the proximal convoluted tubule, any lipid-soluble substances moves through this transcellular route. Anything also moves through the paracellular route as well. Now, what questions do we have about the proximal convoluted tubule? Again, 65% absorbed in the proximal convoluted tubule. Almost all your, most of your glucose, most of your vitamins, your amino acids, proximal convoluted tubule. What we're going to talk about next in the loop of Henle is the reabsorption of salt and water. But what's characteristic about the loop of Henle is an uncoupling of water movement with sodium and chloride. And that's the main idea of what's happening in the loop of Henle. You saw coupling through here, so that main mechanism that I talked about, water moving along with transport of stuff. Here in the loop of Henle, the characteristic, and I won't go into the makeup of the cells, but namely the descending limb, which has cuboidal epithelial cells, is impermeable to ions. It doesn't have any of the channels, it doesn't have any of the co-transporters that we saw prior. So the only thing that it allows that can move down the descending limb is water. Okay? And that water is due to the aquaporins that are present in the descending limb. So how much are we absorbing or reabsorbing? How much water are we reabsorbing? About 15%. 65% in the proximal convoluted tubule. 15% here. By the time we make it down to the loop, we've now reabsorbed 80% of our water. We still have this leftover that we still need to account for, which we'll talk about on the next slides over. The ascending limb, on the other hand, is impermeable to water. And if you look at the structure, and you'll see in any book that you ever look at, they'll draw the thicker squamous epithelial cells that are present as the tubule cells. And this thick layer of epithelial cells makes it impermeable to water, but it allows the movement of sodium and chloride. So again, that uncoupling, water moves down, sodium and chloride move out. And what do we notice? Here you might see the numbers that are also present. You'll see the numbers, and these numbers represent the technically here this is the osmolality, but osmolality, osmolarity, same thing pretty much when you're looking at water. Osmolarity again references the concentration of the solute with that of the volume of water. So something that has a lot of solute and very low volume is going to be hyperosmotic. And that hyperosmotic is going to be a fairly high osmolarity. So what you're going to be able to see is when we go from 300 to 500, 700, and 900 to 1100, we see a rise in osmolarity. What did we see? What did we lose as we moved down the descending tubule?
Water.
We lose water, right? So what's happening to the osmolarity? There's no change in the solute concentration. Why? Because it's completely impermeable to it. What we're losing is water volume. So a decrease in the volume is going to cause an increase in the osmolarity. In other words, if you can think of osmolarity, and let's substitute a better word for it, how salty is that urine getting? So if you can sit there and kind of like taste the urine right there and then like kind of taste it over here, it gets saltier as we move down. And it gets saltier because we're removing water. Take any salty concentration, take salt water and just remove the water out of it, the water's going to get saltier and saltier. And that's exactly what's happening as we move down the length of the descending tubule. Same thing. If we look at the ascending tubule, what's happening in the ascending tubule? Water remains on the inside and it doesn't move. It's completely impermeable to water transport. Now what I'm doing is now I have this salty urine at this point, or salty filtrate. I'm now able to pull sodium and I'm pulling chloride. So now I go from a hyperosmolarity, you get the idea. Hyperosmotic, that's the word I'm looking for. Hyperosmotic filtrate right here. As I start removing salts from it, that's going to bring the osmolarity down. Why is that? Because now I'm reducing the concentration of solutes in the filtrate. So think about, in effect, what am I really doing? Again, uncoupled. I'm removing salt, I'm removing water, and now I'm removing salt. So by the time I make my way up to the top of the ascending tubule, I almost have the same concentration, but I've removed a good amount of water and I've removed a good amount of salt. Does that make sense?
So you had the same concentration at the beginning?
Pretty much. But same concentration, but concentration just tells you the composition of the filtrate, but it doesn't, what it means that by the time I get to this point, I've got also a lot less filtrate. Think about that for a second. I removed water, I removed salt. I'm going to have a lot less of it. So, in this process, I've already mentioned that water moves out through aquaporins. I have to look at how we move sodium and chloride. Because sodium and chloride are going to be the big things that we're trying to move across. So we have to look at the symporters that are present in the ascending limb. Again, we're focusing on the right side, the ascending limb. And how do we get salts across? And the slides here we'll go into. We're going to, again, looking at more images here, and just to quickly reorient you. You're going to be able to see the vasa recta. Again, here you saw paratubular capillaries in the PCT. It's now called the vasa recta in the loop of Henle. But nonetheless, reabsorption still remains the same. It's still moving in that direction from the tubule over to the vasa recta. You're still going to have the same processes, paracellular, transcellular. Now, focusing on the transcellular side, we have to look at what's present. In order to get those ions across, we have to see what's on the apical side as well as the basilar side. Nothing new with the basilar side. You already pointed out earlier, sodium-potassium pump on the basilar side utilizes ATP to push sodium out. The symporter that we have present on the apical side, we have salt, namely sodium, 2 chloride ions, and a potassium ion. 2 positive ions, 2 anions moving across. So still electrically neutral as we move across. Salt we want to move across, nothing changes there. Sodium moves down the same channel. Chloride also moves across and it moves down its concentration gradient once again. Potassium, on the other hand, potassium gets reabsorbed, but it also gets channeled right back out. And this is where we're going to start to get into whether we're going to reabsorb potassium or get rid of it. Now, when we get into the distal convoluted tubule, you're going to see that potassium is kind of one of the exceptions. I did ask a quiz question way back when about potassium. Out of all the things that we looked at, we want to be able to conserve sodium, we want to conserve chloride, because those are the ions that are present on the extracellular fluid. But there's one thing that I mentioned we didn't want high in the extracellular fluid, and that was potassium. Remember when I mentioned before, like people with cardiac issues, they need to monitor their potassium intake because they can't really get rid of potassium, or they produce extra potassium, which we call hyperkalemia. Here we need to regulate our potassium. Potassium we want inside the cell, we don't want it on the outside of the cell. And what helps maintain that? Sodium potassium pumps shuttles it in, but we don't want it too much on the outside. So I don't want to get too much into that, but that's really the main idea. Leakage channels for chloride, because chloride we want to definitely conserve. Sodium we definitely want to conserve. And then the electrochemical drive, same thing. The movement of potassium back out, right? So I get one positive ion in, two anions in, potassium back out. We're going to get an electrical chemical drive that allow other ions to move through the paracellular route in order to maintain electrical neutral movement of ions across.
You said you wanted potassium outside the cell, right?
You want a potassium
Outside?
out? No, potassium you
Inside.
don't want. You want it inside the cell.
Inside.
So while the sodium potassium pumps help shuttle potassium in, we do need to get rid of excess potassium. So in these cases where you see sodium going across, you see chloride going across, potassium might go back into the lumen. It's our way of maintaining that balance. Out of all the ions, yes, potassium, we want a lower amount of it. All right. So let's now look at the whole concept of countercurrent mechanisms. Or should we take a look at 5-minute break? 5-minute break? Yeah. All right, that gives me the chance to hand back stuff to you guys.